Welcome back to section 18.3 in General Chemistry 2. And we are talking about entropy and temperature today. And we're really going to start to get into how do we actually start predicting if something is actually spontaneous? Because we need to know the entropy of the universe, the system, and the surroundings. So system and surroundings will equal the universe. So let's go back a little bit to what we talked about in 18.2. We said spontaneous processes only occur when delta S, so the entropy of the universe, is positive. If we can somehow increase the randomness or disorder of the universe, our process by definition will be spontaneous. And that's equivalent to the change in the entropy of the system. Really, this is like our chemical reaction itself. The system is the reaction, plus the change in entropy of the surroundings. That's what we haven't talked about much before. So this we can calculate, we found out by using the standard entropy values from a table of a reaction. So we can figure this number out. But we need to have an equation to figure this number out so we can actually figure out if something's spontaneous. Now, before we do that, let's think about in which situations or conditions can the delta S of the universe actually be positive? Just mathematically speaking. Well, one, if we think about this, if the delta S of the reaction or system is positive, let's say, I don't know, positive 5 joules per Kelvin, and we add another positive number, delta S surroundings, let's say 10, yeah, we get a positive. So if we have a positive plus a positive, we're always going to get a spontaneous reaction. However, what we might see is, let's say our delta S, the change in entropy of our reaction, is a negative value. So let's just say this actually decreases the entropy of our surroundings. Let's say it's negative 42. So, but just looking at the reaction itself, we might conclude that this is not a spontaneous reaction. However, we can offset that. If we can get a delta S of the surroundings, if we can affect the surroundings enough and increase its entropy such that this number, let's say we get a 50 joules per Kelvin. Now, overall, we still have a positive 8 joules per Kelvin delta S of our universe. And this would still be spontaneous. So, yes, we have an unfavorable or decrease in entropy, but this was offset by enough increase in entropy of the surroundings that overall we still have a positive. So that's a spontaneous situation there. And lastly, what if we have the opposite? Let's say we do have, for a delta S of a system, let's say we have plus 60 joules per Kelvin for a delta S of our system. But we have a negative delta S of the surroundings. So we're actually decreasing the entropy of the surroundings. Let's say this is negative 50 this time. That's still okay because we still get a positive 10 overall. So delta S universe is positive. So that would also be spontaneous. So these are the kind of the mathematical situations where I actually get a spontaneous reaction. If both are positive, this is always going to be delta S surrounding of positive. We can always offset one or the other. So we're going to see how we can offset this. The surroundings really have to do with the enthalpy of the system. And we're going to break all this down. So how do we actually figure out this number? We figured this number out yesterday using a table of values. And if we go back to that table, I have it here. And yes, we have a table of values for delta S joules per mole Kelvin. Just going to quit out of that stuff. But for delta S of our surroundings, we have a special equation. So what we can do we basically simplify our study when thinking of typical everyday reactions. So let's think of maybe a candle burning for a second. And we've got this candle and it's burning here. So this is our reaction, our system. And then we have surrounding it, let's say this is like the building or room. Basically, this little bit of heat doesn't really affect the temperature of the surroundings. Basically, what we call this is an isothermal process. So in an isothermal process, there's no temperature change in the surroundings. It's not like this is insulated by like, a container, but considering the fact that this room or this building is really big compared to this reaction, typically everyday reactions, the one we're going to deal with chemistry, most of them are isothermal processes. So for an isothermal process, we can basically equate the delta S of the surroundings as equivalent to the heat of the system, but divided by the temperature of the surroundings. So that's what it's really equivalent to. This means it's equivalent to the thermal energy of the reaction or system. That's it. So for isothermal processes, we can use this equation. And then at constant pressure, everyday conditions, what we did was simplify this further and to say the heat transfer is equivalent to the enthalpy of the system. And we have tables of enthalpy values. So really what we're going to use, if we need to find delta S of surroundings, all we need to do is get the enthalpy of the system or reaction and divide it by whatever temperature is given. This we can find using tables of values. If I have the delta H information values in this column right here, I can find a value for whatever I need, and I can find the values for the products and reactants and figure out the overall delta H of that reaction. So this is the key equation from this section. Because of it's an isothermal process, we can really think about the delta S of the surroundings. So how much entropy change out here is really just equivalent to the enthalpy change of this little tiny reaction here, divided by the temperature of the surroundings. The temperature is really important here. And so let's look at this equation for a little bit and think about this. So there's our equation. And I'm going to draw another situation here. Let's say this is winter, cold. So you've got the sun, it's basically buried beneath clouds, cold. You can tell it's cold because there's a terribly drawn snowman here. Super cold. And basically think low entropy out here, or small, slow particles in the sky right now. It's really cold. So relatively speaking, a candle actually has relatively high effect. So relatively large effect on entropy, on delta S of the surroundings. Even though this is a small amount of energy compared to the low temperature, so that's why you'll notice delta S is inversely affected by temp. If I have a small temperature here, so whatever the delta H of the system here for a combustion reaction, if I divide it by a low temperature, let's say on a cold day, I get a larger delta S of the surrounding, a larger relative effect. Now, if I look at it the opposite situation, let's say I have a hot day. This is just an excuse for me to show off my skills, obviously. The sun is beating down. You've got, I don't know, say a pool here. Diving board, beach chair, person. I could go on and on and on and impress you with these details, but you get the effect here. It's hot. So relatively speaking, let's draw our candle. How much of an effect is this little candle going to have on these already fast moving particles? Relatively speaking, not as much. And we can do this, we can show this numerically too. Let's say we're going to calculate the delta S of the surroundings here. And let's pretend I already calculated out our kilojoules. Let's say it's an exothermic reaction, so it's a negative. So let's say we have 5 joules per Kelvin divided by, let's say, 0 degrees Celsius. That's 273 Kelvin. So the delta S of the surrounding is going to be whatever that number is. Over here, though, I've got the same amount of energy divided by a hotter temperature. I looked this up, about 38 degrees C is about 100 degrees Fahrenheit-ish. So a really hot day, 311 Kelvin. So which number is going to be the larger effect on the delta S? It's going to be this one, 5 divided by 273. And actually, let me grab my calculator. Let's go ahead and put these numbers down. 0.0183, and this equals 0.0161. So this had the larger effect on the delta S. So depending on the temperature, the delta S of the surrounding value will change. So it's a temperature dependent number. It depends on the enthalpy of the reaction and the temperature at which you do the reaction. So both very important values here. But honestly, really the big important thing to remember is this equation. So we're going to use this equation as an example here. So let's go ahead and do that. We'll scroll all the way down here. And let's add in this no question. Okay, so this is example 18.5. This asks us calculate delta S. So I'm just going to put this down right now. Calculate delta S of surroundings for the reaction of gaseous hydrogen and gaseous oxygen to form 2 moles of water vapor at 298 Kelvin. So that's important. So delta S of surroundings means we need delta H, negative delta H of the reaction, divided by the temperature. Okay, we have this. So we need the delta H of the reaction. So this is step 1. Okay, well, let's do that. Because this is at 298 Kelvin, we're going to be using the standard enthalpy values. So delta H standard formation values from the appropriate table. So if you go back up to the example in the book here, it'll give you the table you need to go to. This is the appendix, appendix A2. So I need delta H formation values for all the things in my reaction. So what is my reaction first? Well, it's like we did in example 18.3. This was 2H2 gas. So I need delta H of formation values, standard formation values for all these compounds. Two moles of H2O, vapor, gas, important. So let's look those up. Delta H reaction, or formation values. So H2, I'm going to jot these down off to the side here. A, B, C, D, E, F, G, H. I did it. H2 gas looks like it is 0. That's fine. It's the pure form of the substance. We've seen that before. It's the elemental form of hydrogen. Oxygen should be the same, actually. It should be 0. The delta H of a formation value of a pure substance, pure elemental form, is 0, 0. And now finally, we need a value for water. We have H2O, gas. Okay, there we go. Delta H formation for water, negative 241.8 units. Joules. Oh, this is in kilojoules per mole. Okay, not joules. That's good to check as well, because the delta S values are actually in joules per mole Kelvin. Okay. So this is 0 kilojoules per mole, 0 kilojoules per mole, and this is negative 241.8 kilojoules per mole. So just like we calculated the standard entropy values, all we have to do is do the products times the molar coefficients plus the reactants times their molar coefficients. In this case, it's just 0. So the delta H of our reaction is 2 moles times negative 241.8 kilojoules per mole minus the values for the reactants. In this case, it is 1 mole times 0 plus 2 moles times 0. So this cancels out. So what do we get? Negative 483.6 kilojoules. Notice the moles cancel out, so we just have an energy value. That's the delta H standard of our reaction. Now we can go back up here and plug this into our temperature, or divided by temperature. So delta S surroundings, and now this is the standard value because we use standard enthalpy values. Temperature was 298 Kelvin. And I'm going to go ahead and do what the book did too. This is in kilojoules. Let's go ahead and get this into joules. So we can just do this here, 1,000 joules in 1 kilojoule, because we want to get this matching the units of our delta S values. So that comes out to 1.62 times 10 to the third joules per Kelvin. So overall, we had a net increase in the entropy of our surroundings here. That's all A actually asked us to do. Calculate delta S for the reaction of the surroundings. So this reaction, as is, overall produces a overall increase in entropy at this temperature. And notice it was all based off the negative enthalpy value. So what happened to our negative enthalpy value? Oh, sorry, I meant to show this negative sign here. That's important. This was a exothermic reaction, negative delta H, and then because we have a negative sign here in our original equation, it turns the exothermic number into a positive number. What that tells us is exothermic reactions equate into increase in entropy of the surroundings. Hopefully that should make sense, because to increase the entropy of surroundings, we're really increasing the temperature, we're creating more movement, more thermal activity, more kinetic motion. So to get that, we really need to get a exothermic reaction. We need to release energy to the surroundings to actually increase the entropy of the surroundings. So a negative enthalpy value, exothermic value here, will cancel out with this negative to give us a positive number overall. If it's an endothermic reaction, then it'll be turned negative, and we'll get actually a reaction that takes away entropy from the surroundings, cooling down the surroundings. So there's our delta S surroundings. Let's go back up here. It says use the results from 18.3 to calculate delta S of the universe for this reaction. Okay, so B. And back to 18.3, we calculated, you can check the last video, delta S of the reaction or system. It was negative 89.0 joules per Kelvin. So the entropy of the actual reaction itself also increased in its randomness. So going from this to this increased the amount of, decreased, apologies, negative value. We got more ordered. We have less randomness. We went from 3 moles of gas down to 2 moles of gas. So yeah, we got less random. So that was the number we got in 18.3. So this question is asking us, though, calculate out delta S of the universe. And I'm going to add to this question is this reaction spontaneous at 298 Kelvin? Remember, specifically, we're working at a specific reaction here. So is this reaction spontaneous? Well, all we have to do is figure it out if that's positive or negative. If it's a positive delta S, it's a spontaneous reaction. So that equals the delta S of the reaction or system plus delta S of the surroundings. So we have all those numbers now. The delta S of the reaction was negative 89.0 joules per Kelvin. And the delta S of the surroundings was a large number. So yes, this turns out to be positive 1530 joules per Kelvin, spontaneous. At 298 Kelvin, that is. Now, see what happened here? The reaction itself actually we had a decrease in randomness, but this huge payoff of entropy from the exothermic part of the reaction made this a spontaneous reaction. If we look at this reaction again, the reaction itself, we're combining 2 moles of this gas plus 1 mole of this gas, so that's 3 total moles to produce only 2 total moles. That is less random. This is more order. That is, energetically unfavorable. But the big exothermic payoff, this comes from the energy tied up in the bonds, this was favorable. So that turns into a large delta S of surroundings increase, which offsets this negative number to give us overall positive delta S of the universe. So that's really what this section comes down to. Now we can calculate delta S of a reaction using the values in the table, and we can calculate delta S of the surroundings using the enthalpy values, the delta H values in those tables, to get an overall picture of whether or not this is going to be spontaneous. And notice the temperature would change the situation. I divided this exothermic value by 298 Kelvin. What would happen if I did this in a really, really, really cold room? This number would drop even farther and have a much higher effect on the entropy, and it'd be even greater positive number. But what if I did this in a really, 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 really hot room? Let's say I did this at 483 kilojoule, or sorry, 483 Kelvin. It'd be this number turned into a 1 times 1,000, so that would probably still work. But the hotter this gets, the smaller effect it has in delta S's surroundings. So that's why you have to include this temperature value. Temperature is connected to entropy on this side of the equation, not on the actual delta S, the reaction, the system side. So let's go ahead and get one more photo. Is that it? That is not it. I wanted to bring in the section review. There it is. For you guys to take a look at. So here's what we learned about in this chapter. We have this equation here. If it'll allow me, please allow. Delta S, the universe, is equivalent to the system's enthalpy plus the surroundings. This has to be positive for a spontaneous process. So we can calculate delta S, the surroundings, right here using the enthalpy of the system or the reaction divided by temperature. This comes from, if we're using the standard values from the tables we can look up, this also comes from the standard values of the table we look up. Negative delta S reaction values can be offset by large delta S surrounding values, basically exothermic reactions, making our delta S of the universe positive overall. All right, guys, hopefully this helps you get through these problems, and I will see you next time for section 18.4.